Okay, done. First part, right. So, second, a spring that obeys Hooke's law has a spring constant K. Show that the energy E stored in the spring when it has been extended elastically by amount X is given by E is equal to half Kx square. Look, the spring, the object is obeying Hooke's law, then the force extension graph will be straight line. And the gradient of this will be the material constant, the spring constant, but the area which is equal to 1 by 2 base into height is the energy. So energy is equal to 1 by 2 Fx, but according to the Hooke's law, F is equal to Kx, so E is equal to 1 by 2. Instead of the F, we can write Kx, then X. So finally, energy is equal to 1 by 2 Kx square. It's proved. But there is another method. This energy, elastic potential energy, is equal to work, and the force is not fixed. We start from the zero, we continuously increase the force. So average force multiplied by distance covered by the spring. So the average force initial 0, final is F divided by 2, and the distance covered is extension X. So energy is equal to half Kx, and then F is equal to Kx. So 1 by 2, F is Kx into X, half X square. So use either this method, graphical, or this average method for the work. Done? Okay. Next C part is a light spring of unextended length, 14.2 centimeter, is suspended vertically from a fixed point as illustrated. So this is unloaded spring. When it is loaded with this load, its extension becomes 16.3, mean the total length becomes 16.3. So the extension will be 16.3 minus 14.2, it is 2.1. And then further, it is extended by the extra force F, additional force F. So the extension is 3.6 minus 2.1, right? The question is, a mass of the weight 3.8 Newton is hung from the end of the spring as shown. The length of the spring is 16.3. Additional force F then extend the spring and the length becomes 17.8 as shown. Spring obeys the Hooke's law and the elastic limit is not exceeded. Show that the spring constant 1.8 Newton per centimeter, not meter. So Hooke's law is F is equal to Kx. K is equal to F divided by X. F force load is 3.8 and the extension for the first load 16.3 minus 14.2 is 2.1. So the answer is 1.8 Newton per centimeter. Any question? No? Okay. Now move to this next. For the extension of the spring from the length of 16.3 to the length of 17.8. From this second diagram to this third diagram, calculate the change in gravitational potential energy of the mass. So the change in gravitational potential energy is mg delta h. So mg together is the weight. So weight is 3.8. And what is the change of height? 17.8 minus 16.3. This is in centimeter, so we have to convert this into meter, divided by 100 or 10 power minus 2. So the answer is coming 0.057. Any question? No. Okay. Next, show that the change in elastic potential energy for these two lengths 0.077 joule. So we will calculate first energy 1 by 2k x 1 square 1 by 2, and the k is 180 Newton per meter now. And the change of the length, the first extension is 2.1 centimeter. So 10 power minus 2 whole power 2. And the answer first is 0.0396. Now the second energy, 1 by 2 k x 2 square 1 by 2 180, and the final length minus the initial length 17.8 minus 14.2 centimeter to meter 10 power minus 2 square. This is coming, and then the difference of these two is the change in elastic potential energy. Yes, 1.8 is given Newton per centimeter, so which is now 1800 Newton per meter, right? Yeah, so Newton per centimeter. So per centimeter division is multiplication. Now determine the work done by the force F. Look, the work done is the difference of elastic potential energy and the gravitational potential energy. This is the change of potential energy and elastic potential energy. The difference is the work done, 0.02 joule. Right? Next question. Tensile force. Yes, it's different from the normal force. Tensile forces are applied to the opposite ends of the copper rod so that the rod is stretched. The variation with stress of the strain of the rod is shown. Use the figure to determine the Young modulus. This is stress strain graph. So the gradient of the graph is the Young modulus. So gradient delta y over delta x. So what is the change in y-axis? From 0 to, suppose this point, this is 2 into 10 power 8, right? And the x-axis distance covered is from 0 to this one, it's 1.8 into 10 power minus 3, and this is 10 power 8. So 2 into 10 power 8 divided by 1.8 10 power minus 3. After the calculation, the answer is coming 1.1 10 power 11 Pascal. This is Young modulus, okay? Next, on the figure 5.1, sketch a line to show the variation with stress of the strain of the rod as the stress is reduced from 2.5 into 10 power 6 is written, but we have to take it 10 power 8 because the graph is plotted for 10.8. So here is a mistake in the printing mistake. So 2.6 into 10 power 8 Pascal to 0. No further calculation are expected, mean it is extended to this stress, which is 2.5 into 10 power 8, mean this value. So it is at this point, and we have to unload it. So while unloading, we will draw a line which is parallel to the previous, because the Young modulus while loading and unloading will remain same. The Young modulus is the gradient, so parallel line. So you have to draw this parallel line. Okay, so the next, the ball of the tires on a car can made of the rubber compound. The variation with the stress strain of a specimen of this rubber compound is shown. As the car moves, the wall of the tire bends and straightens continuously. Use the figure to explain why the walls of the tires becomes warm. We have done that. Rubber does not obey Hooke's law, and some of the energy is not delivered, not released at the end. It is absorbed by the rubber as a heat. So energy supplied in stretching is greater than the energy released during straightening. So the remaining energy is absorbed as thermal energy, which causes the increase in temperature. So this loop area is showing the energy which is absorbed by the rubber. We have done in the theory class. So this energy which will cause the increase in the temperature or the change of the temperature. Next, question number 3. A uniform length, wire length L and the constant area A. The material of the wire has a Young modulus capital E and the resistivity rho. A tension F, mean the force in the wire causes its length to increase by delta L. For this wire, state expression in terms of L, A, F, delta L and rho for the stress sigma, force divided by area. And strain epsilon, delta L over L, extension divided by original length. And the Young modulus E, extension is delta L. So stress divided by strain, stress is force divided by area divided by strain, mean multiply by L divided by E. And then resistance, look, in O level we have done resistance directly proportional to length, inversely proportional to area. So resistance is equal to constant L over A. And where this constant rho is called resistivity, hence R is equal to rho L over A, and rho is given here. This is not the density, this is the resistivity of the wire. Next, one end of the metal wire of the length 2.6 meter and the constant area of cross section 3.8 10 power minus 7 meter square is attached to the fixed point. The Young modulus of the material is 7.0 10 power 10 and its resistivity is 2.6 10 power minus 8 ohm meter. The load of 30 Newton is attached to the lower end of the wire, assuming that the area of the cross section does not change. For this load of 30, show that the extension wire is 2.9. So extension, Young modulus, F over A multiplied by L over E, mean E is equal to FL over AE. F force 30, length 2.6, area cross section 3.8 10 power minus 7, Young modulus 7 into 10 power 10, and after the calculation 2.9 into 10 power 3 meter, which is 2.9 millimeter, hence shown. Next, calculate the change in the resistance of the wire. So look, we have done that R directly proportional to L, then the change of resistance will be directly proportional to the change of the length. So the change of resistance and the resistance ratio is equal to change in length divided by length, right? So both are equal to the strain. Hence the change of resistance is equal to change of length divided by length, multiply by resistance. Now use this formula. Change in length is 2.9 10 power 3 divided by original length 2.6 and multiply by the resistance is given here. No, first we have to calculate that. So look, R is equal to rho L over A. Rho resistivity is given 2.6 10 power minus 8. Length is 2.6. Area is 3.8 10 power minus 7. And the resistance is given 0.178. So multiply here 0.178. You will get the answer 1.98 10 power minus 4 ohm. This is the change of resistance. Look, the area is given here. This one. Next. The resistance of the wire changes with applied load. Comments on the suggestion that this change of the resistance could be used to measure the magnitude of the load on the wire. Suppose this is the wire. And it is connected with the ohm meter, which measures the resistance. When this wire is loaded, the wire is under stress, change in length will cause the change in resistance. So there will be deflection on the meter. If this ohm meter is calibrated into Newton, So it will measure load. If this ohm meter is calibrated into kilogram, it will measure the mass. So extension directly proportional to load and delta R directly proportional to extension. So the delta R directly proportional to load, it means we can measure the load, we can measure the mass by calibration of the ohm meter, and that instrument is called strain gauge, bathroom scale, personal scale. That is the strain gauge. Next, number 4. A metal wire has a spring constant K. Forces are applied to the ends of the wire to extend it within the limit of Hooke's law. Show that the extension X, the strain energy E stored in the wire is given by this. So look, this is repeated. We have already done 4 marks. Next. The wire in A is now extended beyond the elastic limit, the force causing the extension, and remove them. The variation with extension of the force given. So this is a graph. The question is, energy ES is expended to cause the permanent extension in the wire. Shade the area that represents that energy. So this loop energy, which is shaded, is the energy which is used for the permanent deformation because it is absorbed by the material. Okay, so this shaded area is the energy absorbed by the material for the permanent deformation. Then the question is, calculate this energy. So first we have to calculate the area represented by the large square. This large square has 100 boxes and its area is 20 multiplied by 0.2 millimeter. So 20 multiplied by 0.2 millimeter. So the 100 boxes area is 4 into 10 power minus 3. These are the 100 boxes, 4 into 10 power minus 3. And then we will count the number of the boxes of the shaded area, and they are coming 45 plus this, and approximately they are 135. You have to count half and above box. If it is covered, it is covering less than half box, ignore it. So they are approximately 135. So how much area is covered by 135? So here the calculation, 4 into 10 power minus 3, divide by 100, multiply by 135. This is the answer. So it is 5.4 millijoule. So look at this. Suggest the change in the structure of the wire that is caused by the energy ES, permanent deformation due to stored energy as thermal energy, which increases the molecular spacing. Permanent deformation. And also increases the amplitude of the vibration of the solid. Next to that. Question number 5, define for a wire the stress tensile force exerted per unit cross-sectional area is called stress. Strain ratio between extension and the original length of the material is called strain. And then a wire of the length 1.70 meter hangs vertically from the fixed point. The wire has a cross-sectional area of 5.7, 4 10 power minus 8, and is made of a material that has a Young modulus 1.6, 10 power 11, load of 25 newtons is hung from the wire. Calculate the extension. Young modulus, stress divided by strain, F over A, L over E, mean E is equal to F L over E. F is 25, length is 1.5, area given, Young modulus given. So the answer is coming 4.6 into 10 power minus 3 meter. This is the extension mean 4.63 millimeter. Next. The same load is hung from the second wire of the same material. This wire has twice the length but the same volume. as the first wire, state and explain how the extension of the second wire compares with that of the first wire. Look, volume is area into height. When volume is constant, area and height both are inversely proportional. When length becomes double, the area becomes half due to the constant volume. Extension directly proportional to length, extension inversely proportional to area. Due to double length, double extension. Due to half area, double extension. So the total extension becomes 4 times more than the previous. So it becomes 4.63 into 10 power minus 3 times 4. Length double, extension double. Area half, again double. So total becomes 4 times. Next, that's it.